with some problems from the past exam papers. I posted on Moodle the exam papers from 2010 to 2015 and complete solutions for the 13, 14 and 15 exams. That's the vector and the complex half. So in the exams I'm going to concentrate on questions from the 2010, 11 and 12 papers. I'll begin with this one here, which is from the 2010 paper, question 4. Most of the time during this video I'll not be writing up the question just to save time, so if you're watching this as a recording, find time to get your hands on the exam paper so you can at least look at what the question is. So this is a basic mapping problem under a linear fractional transformation, the sort of thing I did in some of the short videos as well. And we're looking at the image of mod z minus 1 equals 1, which is the circle I've drawn in green here, under w is z over z plus 2. Remember, the standard way of doing these things is to invert the problem. So we basically solve this for z. So we have z is, and I actually worked this out beforehand, 2w over 1 minus w. And we substitute this into that equation. Now, since the singularity of this linear fractional transformation is at minus 2, which is not on the circle, we're actually going to get another circle out at the other end, not a line. So putting this in, the image is given by 2w over 1 minus w minus 1. Modulus of that is equal to 1. So we rearrange this, multiply up by 1 minus w, and I get modulus of 2w minus 1 minus w is modulus of 1 minus w. Rearrange this. This is going to be a circle. As I say, we're going to square both sides. The next step, put this here, i.e. modulus of, notice 3w minus 1, we might as well put the square in at this point, is w minus 1 squared, or w minus 1, same as mod 1 minus w naturally, and with the usual notation that w is u plus iv, this is going to be, well, that's going to be 3u minus 1 all squared plus 3b all squared is to equal u minus 1 all squared plus v squared. Squaring out, rearranging, what have we got? We're going to have a 9u squared and a u squared on that side, so it's going to give me 8u squareds and 8v squared as well. It's telling me it's a circle, and I'm going to get a minus 6u from that and minus 2u on this side, so it's going to leave it with a minus 4u there. The constant terms will cancel themselves off. So that's our image curve. Divide through by 8, complete the square. And that's going to be, what's going to be u squared minus a half u, so that's u minus a quarter all squared plus v squared equals, well, it's going to equal a 16th, otherwise known as a quarter all squared, which you can clearly see is a circle. Circle centered at the w is a quarter, radius a quarter, so it's again going to go through the origin. So it's going to go, a little circle in there, the centre of the quarter. I won't bother writing that in. We see the point 0, which was on the original circle, is on the image circle, but that's correct because if you put z equals 0 in here, you get w equals 0, and well, you can check. I mean, the point where z equals 2 gets mapped to, in fact, it gets mapped to the point where w is a half, so that's all right. So everything has just been shrunk in that way. So that's the image of this circle. Okay. The question didn't actually ask for a diagram, but obviously you'd want to draw one just so you know what you're doing. Now the next question I'm going to look at is actually from, it's another mapping sort of problem from the tutorial problem set question 44, which is looking at mapping under the hyperbolic sign. And the question asks, for those of you who don't have access to the problem set, what happens to lines where V is constant, Z is, real part is constant, imaginary part constant, and then putting together that into something else. So, what is now dry enough. This is question 44. We're mapping hyperbolic sign, which is, I'll write this down, I always have to remember, write these down, remember, sin x cos y plus I cos x sin y. So the question asks, I'll get my notes together. But the first part asks what happens, I said, for the real part being constant. If the real part of z is c, then w, which is to be sin of z, or w, remember, is u plus ib as usual, u will be sin of c times cos of y, and v will be cos of c times sine of y. The question is, what's that as a curve? Well, if we divide through by the appropriate hyperbolic parts and square and add, as long as the c is not 0, we're going to get what's going to be an ellipse, in fact. So if c is not 0, because that's the only time cos or sine vanish, c number is real, we get u over sine all squared plus v over cos all squared is 1, i.e. that's an ellipse. If c equals 0, well, u equals 0, and v is just sine y, so we just get part of the imaginary axis between I and minus I, we get that, in fact, the sine of y will vary from +1 to -1 as y varies across the whole real line. All right? So that's what happens if the real part is constant. Second part asks us what happens about the imaginary part. So, imaginary part is constant at d, then u is, what have we got here? We've got sin of x cos of d, v is cos x sine d. Now if the cosine and the sine are neither of them 0, we can divide through by them and square and subtract using the hyperbolic Pythagoras identity, and we get a hyperbola, part of a hyperbola, which part will depend on whether the cosine and sine are positive or negative. And we don't want to go through all the details of that. If cos d sine d not 0, we have, well, it's going to in fact be v over sine d all squared minus over cos d all squared is 1. That's hyperbola. If cos d equals 0, that's at odd multiples of pi on 2, we Sine here is going to be plus or minus 1 depending on which multiple of pi on 2. So v is just going to be cosh. It'll be from 1 to infinity or from minus infinity to 1 depending on the sign of the sine. If sine d, sorry, I did the cos first, I was talking cos there. If cos d equals 0, u equals 0, a is plus or minus cosh x. That's part of the imaginary axis from I upwards or minus I downwards. If sine of d equals 0, then v equals 0, and u is plus or minus sine. Well, that doesn't actually make too much difference because the hyperbolic sine varies from minus infinity to infinity, so you'll get the whole real line forwards or backwards depending on the sign of this sine here. Okay, so that's what happens for the curves constant. I'm not going to write down and go through all the details here. It's interesting, by the way, if you have access to a computer with Maple or MATLAB or Mathematica, you can actually animate this, and as d varies, you'll see these shapes varying from I upwards. They'll open out to parts of hyperbolas, they'll become the real line, and then they'll become the other half of hyperbolas and close up. It's an amusing thing to animate if you feel up to it. Okay. So that's the first part of it. The second part of the question is asking for what happens to certain strips, certain parts of the complex plane under the same transformation. But having done these, we can put more or less everything together. Just take that one out for a moment. I'll just do this one in pictures, I think, rather than write everything down. Part 3. They're actually called A, B, and C. Never mind. The third part. Let's get the right numbering. It's the strip here for the real part. Use green here. Real part of z positive, and the imaginary part lying between 0 and pi on 2. So this part of the complex plane. Ask what does that get mapped to? Well, we'll find another black pen. Well, we've already done essentially everything we want. We just look at what happens to the edge of the region here. The first part to look at is this bit here, where the real part is 0, and the imaginary part lies between 0 and pi on 2. Remember that got mapped to part of the imaginary axis, and because we're not going all the way from minus pi on 2 to pi on 2, we'll in fact only get from 0 to I. So that part of the edge of the border region gets mapped to that part. This part here, where the imaginary part is 0, well, I've already got the thing up here. That's, of course, what happens when sine of d is 0. And so we're just going to get u equals, in this case it'll be plus because the cosine is 0. We'll just get the hyperbolic sine of x, but x is positive, so we'll only get the real part. We'll get this part here. So that's what happens to that edge. What happens to that top part here? Well, in that part, again, the imaginary part is constant, but this time at pi on 2. So the cosine part is 0. The sine is going to be 1. Have I got that the right way around? I might have got it right around. I've just forgotten exactly what I said. But what you will get is you will get this part here, certainly, and you'll get V is cos x. So as x varies along here, we'll go up the imaginary axis. So in fact what we'll get is the entire first quadrant. That bit's got mapped to the real line, that bit's got mapped to that part of the imaginary axis, and this bit's got mapped to that part of the imaginary axis. Okay. This corner here is preserved as a corner, and that one is not. I talked briefly in lectures about conformal mappings, and if you remember what I said there, if you've studied conformal mappings, you'll see why that's the case. Okay. So that's what happens to that bit. The other one is looking at a similar strip, but going in the other direction, and y going from minus pi on 2 to pi on 2. So it's part D. Was where my notes just gone? Just got my notes, but I lost them. Here they are. So the imaginary part's going from pi on 2 to minus pi on 2, and the real part negative, so that's semi-infinite strip going in this direction. And what does that get mapped to? Well, make sure I've got room to let me draw it down here. Much the same game as before. That part we already know, that gets mapped to as over here between 0 and I up the imaginary axis, and this part will get mapped to, that's minus pi on 2 there, of course, from 0 down to minus I. If you look back to the formulas that I had, since I'm varying the imaginary part from minus pi on 2 to pi on 2, I'll get the whole range of sign. Do it that way. So we're going from minus I to I. That's what happens to that. What will happen to that? Well, in fact, it'll be very similar to what happens to that one there. In fact, it'll be identical if you look back to the formula. I'm just going to get everything up. Because it's actually the cosine, it's the hyperbolic cosine I want, and hyperbolic cosine's even, so whether the real parts positive or negative doesn't make any difference. I'm still going to get everything up here. That's what happens to that top line. And as for the bottom line, well, you put it all into the formulas I've got, and you find that I get essentially minus the hyperbolic cosine for V, so that's everything down there. So I'm going to get, well, that's what happens to the edge. The question is, which one of those half planes do I actually get? The one on the left or the one on the right? Well, you can sort of try and nut that out, but the quickest way of spotting that is to ask yourself, what happens to a certain value? I mean, I'm not going to have part of this region go to this part that's, it's all on one side or the other. So if we look at what happens to a number like 1, what happens to 1 under the hyperbolic, sorry, minus 1, happens to minus 1 under the hyperbolic sign, well, it goes to sine minus 1, which is a negative number, so that's sine minus 1, somewhere over there. Don't know exactly where, don't really care. But that's telling me I must get, in fact, the left half plane, not the right one. Okay. So the hyperbolic sign maps that strip to that half plane. Right. say the next question I'm going to be looking at is actually from the 2011 paper, question 5, part 3, which is I think on the integration, if memory serves. No, just clean this off. See if there are any messages here. No, just a few messages deleted. Section 3. We're given two contours, a line segment and a semicircle, and we'll have to evaluate the real part of z, integral the real part of z over the line segment, and the integral of sine z over the semicircle. So let me just, first one, integral of gamma 1, real part of z dz. Gamma 1 is the line from 1 to 3 plus I. Okay? Now, because we're integrating the real part of z, we can't use antiderivatives or anything like that. We just have to do it the basic way, which is parameterize the contour. And since it's a line, that's not too difficult. I'll draw a picture. Well, why not draw a picture? Just to show willing. We're going from 1 to 3 plus I. That's our contour. Gamma 1 parameterize as gamma 1 of t is going to be 1 plus t times, well, the difference between 3 minus I and 1 is 2 plus I, t between 0 and 1. Alright, so the integral of gamma 1, real part of z dz, integral from 0 to 1. Well, the real part of this thing here is just 1 plus 2t. Z, remember, we're going to do a change of variables, so we multiply by gamma 1 dash, which is 2 plus I. Dt, that's correct, is, well, 2 plus I is just a constant, so it's 2 plus I. Well, we're going to integrate 1 plus 2t, that could hardly be much easier. T plus t squared between 0 and 1. Well, t plus t squared is 2, so I'm going to get to 2 times 2 plus I. Right. Straightforward line integral. Okay. Not designed to test you on your integration skills, designed to test you on can you actually, write down the line integrals, you know what line integral means. Right. Part B asked for the integral on gamma 2 of sine z dz, where gamma 2 is the semicircle centered at pi on 2, of radius pi on 2, taken anti-clockwise from pi to 0. Well, I'll just draw a picture of that, I think. Centered at pi on 2, radius pi on 2 from pi to 0, so starting at pi, centered at pi on 2, taken anti-clockwise. It's that way. Okay. Now you could try parameterizing this, of course. Just z is going to be pi on 2 plus pi on 2 e to the it for t from 0 to pi, and shove that in. That's going to be pretty much a nightmare. So we don't do that. We of course use an antiderivative, because we've got a function whose derivative is sine, minus cos is the thing we want. So this is just going to be minus cos of z at the initial point of pi minus the value of the original point, or the end point 0. So that is minus 1 minus cos of pi is minus 1. Is that? So I'm going to give us 0. Is that the right answer? No, minus plus 1, minus 1, but next to minus 1 missed off, so it's minus 2. That's more like it. So that's a question in recognizing that this is an analytic function, so it has an antiderivative, so we use the antiderivative. Hopefully that's right. The next one I'm going to look at is the next part of this question, part 4 of question 5, on residues and poles, I think. Yes, residues and poles. I'll leave that half up for the moment. So the question said, showing your working, find the order of the pole at z equals 0 for the function f of z, which is z squared all over e to the z minus cos z minus z, and then what's the residue? We're looking at, say, z equals 0. Well, I mean, we can write down the series for e to the z and subtract off the series for cos, and then the z, and you're going to get a series for what you want there. And that's probably going to be the quickest way through, to use index accountancy to look at the order of the 0 on the denominator and subtract it off the order of the 0 on the numerator, because clearly we've got a 0 of order 2 here on the numerator, z squared. So what's happening on the denominator? Well, you could write it all out, or you could use the fact that e to the z minus cos z is in fact the hyperbolic sine. If you can remember your series for hyperbolic sine. I'll not do that. I think I'll just do it without trying to be too clever here. Note e to the z minus cos z minus z, because we only need the first 2 or 3 terms in each series. Is, well, e to the z is 1 plus z plus z squared on 2 factorial, and we'll in fact need that one as well, minus the series for cos, which is 1 plus z squared on 2 factorial plus z to the 4th on 4 factorial, etc., minus the z. And we can see that the 1's cancel off, the z's cancel off, and the z squared on 2 factorials cancel off. The first term that doesn't is that one there. Cubed on 3 factorial. I got the series for cos right there, yep. And in fact, the next term well, the z to the 4th and 4 factorials will cancel off. The next one that will survive will in fact be the z to the 5 and 5 factorial, plus and so on. So e to the z is got that as its Maclaurin series, since we're beginning with the z cubed. We see that the denominator has 0 of over 3 and z equals 0. Refresh my graph here. So I've got a 0 of order 2 on the numerator and a 0 of order 3 on the denominator. So that gives me, well, 2 minus 3 is minus 1, a 0 of order minus 1, better known as a pole of order 1. So let's write that down as numerator that's a 0 order 2. As far as an exam situation would go, I would take that as obvious. You didn't have to really prove here. 0 of order 2 f of z. So I can the board's a little damp. I've done that. Has a pole of order 1 equals 0, also known as a simple pole. All right. Now we're asked for the residue, and one could, well, the formula for the residue says that it's a limit as z goes to 0 of z times f of z. And you could do that here. You'd get z cubed over the e to z minus and so on. Then you'd have to use L'Hopital to find that residue, but to do that from scratch you'd have to use L'Hopital 3 times. Bit of a drag. But in fact we can make better use of the series calculation we've just done, so I did it this way. Residue z equals 0 is by definition the limit as z goes to 0 z f of z, which is the limit as z goes to 0. Write this in terms of its series. We've got a z cubed on, well, let's just write down the series thing here, z cubed on 3 factorial plus z to the 5 on 5 factorial plus, etc. We can see we can just now cancel off the z cubed numerator denominator, and we can now send z to 0 happily, because we're just going to be left with 1 upon 3 factorial on the denominator. So this is going to be 1 on 3 factorial, better than 6. That's the residue. And I invite you, if you feel sufficiently masochistic, to go through and do this with L'Hopital's rule. You'll see you need to go through it 3 times. No comments coming in. Now, I was asked to do a number of questions involving calculating residues and doing integrations by residues. I'm going to do one of them next, again from the problem set, problem number 94D, because it illustrates a useful little technique in calculating residues, particularly when you're calculating multiple residues of things like trig functions, which is what that question's about, if you look at it. in. And so this is the integral around mod z is 9, z cubed times z. Just double checking that from my problem set 94. That's correct. All right. Well, the first question is, where are all the singularities? Mod z is tan has singularities where cos vanishes. Cos vanishes at odd multiples of pi on 2. The question: how many multiples of pi on 2 do you find in mod z equals 9? Well, the answer is, in fact, you get 6 of them. Right. Well, then one at pi on 2. There's one at minus pi on 2. Pi on 2 is about 1.5. 3 pi on 2 is the next one. And of course, the one at minus 3 pi on 2. 3 pi on 2 is about 4.5. The next one along will be at 5 pi on 2. 5 pi on 2 is about 7.5. That's going to be inside. 5 pi on 2 and minus 5 pi on 2, so that's a bit small. The next one will be at 7 pi on 2. But 7 pi on 2 is, 7 pi is about 21, 22, so that's about 11 or something, so that's outside. So we've got 6 singularities inside the contour to calculate the residues at, and residue theorem says that this integral will be just the sum of the residues multiplied by 2 pi I. The question is, what's the best way of finding these residues? Well, the first thing we need to know is what sort of singularity we've got. Let's define the function properly. Let's let f of z be z cubed tan z, which remember is z cubed sine z over cos z. And cos we know has simple zeros, we ought to know. Cos vanish, where cos vanishes, sine doesn't, sine being the root of cos, so the zeros are simple. So we've got simple zeros, 1 over a simple zero is a simple pole of order 1, put it another way. So we have simple poles at, well, I'm going to use an abbreviation. I'm going to say, let's let zk be an odd multiple of pi on 2, k of course, being an integer. Right? And I'm going to find the residue at each of these zk. Or I'm going to do all at once. I'm just going to write a formula that will get me them all. And we'll see that I want k being 0, 1, 2, minus 1, minus 2, and minus 3. That's the ones I'm going to need. On the residue, z is zk. See, the handy thing here is this abbreviation saves me having to keep writing this sort of stuff down. Okay. Piece of tactics, really. Residue of f, limit z goes to zk, and z minus zk, z cubed sine z over cos z. Now it's a 0 over 0 thing, so it looks like L'Hopital, but again, this is the sort of thing you should be on the lookout for, these sorts of residues in calculating them, either in the exam or in actual practice. The z cubed sine z behaves perfectly well as z approaches zk. It tends to something finite. So we'll move that outside the limit. That's the limit of product is product of limits problem. Well, it's a theorem that you all want to know. So this is equal to, well, let's just write it as zk cubed times sine of zk. This will be plus or minus 1. sine of 2k plus 1 pi on 2 is just a fancy way of writing minus 1 to the k. But I'm going to leave it as sine zk at the moment. For reasons that will become apparent when we get to the end here, times the limit as z goes to zk, z minus zk, sorry, that's just meant to be minus sign over cos z. Right? And that's now in the right sort of shape for a nice simple L'Hopital. 0 over 0, both top and bottom, numerator and denominator are analytic, so L'Hopital's rule applies, and it tells me I just need the derivative of that divided by the derivative of that, assuming that derivative exists, which that limited derivative exists, which we can easily see it does. So this thing here is zk cubed sine zk times the limit as z. So it goes to zk 1 over, well, the derivative of cos is minus sine z. Sine behaves properly at this point. So what we're going to get, I'm just going to get minus 1 over minus sine zk, which cancels off the sine zk here. So you see why I left it as that rather than writing it as minus 1 k. Not really made much difference. So this is zk cubed sine zk over minus sine zk is minus zk cubed. So that simultaneously got me the residue to all these poles. Hence, the integral of my function is 2 pi I times, I'm just going to add up, these are the zk's here, just cube all of those. So I'm going to get pi on 2 cubed plus 3 pi on 2 cubed plus 5 pi on 2 cubed plus minus pi on 2 cubed. What's going to cancel off? Well, in fact, you can probably see that they're all going to cancel off. And in fact, the answer is 0. 0 not because the function is analytic, but because all the residues cancel off. Okay. Have any comments from anybody? Right. So next, I'm just going to do 2 more questions, which will probably take me over the hour, but we'll get them through. We'll do an example of an integral along the real line, which I didn't get to do as one of those little videos because I just didn't think I could fit it on the whiteboard, so we'll see if I can. And then we'll do an integral from 0 to 2 pi. That'll probably take me past the hour, so apologies. There's a couple of questions people asked me to look at. I don't think I'll have time to do. If there's 2 problems you want me to go through, then come and see me sometime before the exam, and I'm happy to go through them with you. All right. So let me just clean this whiteboard off. The ones I'm going to do are from the one from 2012 and one from 2011. So let's sip of water before we do another one. All right, 2012. Question 6, part 2. And basically, although the question is worded with a bit more help, we're actually calculating this integral here, the integral from minus infinity to infinity cos x over x squared plus 2x plus 5 dx. The question actually asked you to consider a certain integral of e to the z over z squared plus 2z plus 5 over what it refers to as the standard semicircular contour. So let's let f of z be e to the I z squared plus 2z plus 5. We find the integral of f of z. Now I'm going to use the notation I used in the lectures. Gamma r is LR plus CR, where LR, remember, is the line from minus r to r, and CR is the semicircle in the upper half plane from r to minus r. Usual picture. CR and LR along the real axis. And the game, remember, is you find you calculate this thing here by making sure R is big enough to include all the residues inside. You send R out to infinity, you prove that the integral along CR tends to 0, so what you get is a thing that's actually called the Cauchy principal value of this integral, but because the integral exists, that's first year work, because of the shape of it, because it's a cos over a quadratic, and the Cauchy principal value equals the integral, and that's how you get the answer. Alright, so the first thing to do is to find the poles. Well, in fact, the question, if you have the paper in front of you, one of the roots of z squared plus 2z plus 5 is minus 1 plus 2i, so you're actually given that. Minus 1 plus 2i, so we've got one of the singularities here. The other one, of course, will be down there, minus 1 minus 2i, because it's a real quadratic, so the roots occur in conjugate pairs. Since we've got two distinct roots, I must have two simple zeros here. It must be z minus this thing and z minus the other. It's a factorization. So simple zeros on the denominator means we've got simple poles of the integrand. Well, let me make a comment about that. Find that, what gamma r is that? Shown. So the only singularity of f inside gamma r is at minus 1 plus 2i, which, as I said, is a simple pole, because it's 1 over a simple 0. So we need the residue there. Do I say anything more? Oh, assuming, of course, that r is big enough that it includes minus 1 plus 2i, so r is bigger than root 5. We're going to send r out to infinity, so r bigger than root 5 is not really a problem. So do I have room to fit the calculation of the residue down the bottom here? Oh, probably. Residue z is minus 1 plus 2i f of z, limit as z goes to minus 1 plus 2i, z plus 1 minus 2i f of z, usual formula. Well, we could factorize that easily enough. Factorize, cancel, just not writing down an intermediate step here. It is the limit z goes to minus 1 plus 2i, e to the I z, and the other term will be z minus 1 minus 2i, no, z plus 1, sorry, plus 2i, minus 1 minus 2, yep, which is, let me put it out here, so the residue of f is, I'm going to get e to the I times minus 1 plus 2i is e to the minus 2 times e to the minus I, e to the minus 2 minus I, divided by 4I. Okay. So that's the residue, and then the integral of f along gamma r, the residue theorem, is 2 pi I times that, so I'm going to get pi times e to the minus 2 e to the minus I divided by 2. Now when I want to find the answer is going to be the real part of this, because what I want is really the real part of the integral of e to the ix. So the answer is going to be pi over 2e squared times cosine of 1. I've not proved that fact yet, I just know that's what the answer is. Right? To prove it, I've got to get rid of I've got to prove that as r tends to infinity, the integral along CR tends to 0. Well, this again is fairly routine. On CR, mod z is r because it's a semicircle radius r set to the origin, and the imaginary part of z, e to the minus y, is bigger than or equal to 0. So the modulus of the e to the iz, that's the numerator, that's the e to the ix minus y, which is e to the minus y because e to the ix is a complex number on the unit circle. E to the I times anything real has modulus 1. So e to the minus y, and that's less than or equal to 1 because y is less than or equal to 0. That's the numerator taken care of. What about the denominator? Well, two ways of doing this. You could use the circle inequality, but given we've got 3 terms here, that's going to be a bit awkward. So I'm going to use the other method I mentioned in lectures, so basically using the idea of actually making use of the definition of limit for our own purposes. Clearly, well, it behaves like z squared, at least the numerator does. So we know that z squared over z squared plus 2z plus 5, the modulus, that tends to 1 as mod z tends to infinity. Right? So if this thing's tending to 1, and it's clearly positive, eventually this thing will be less than, well, 2, or 1.5, or 1 whatever you want. We'll pick 2. So eventually this thing will be less than or equal to 2 for large mod z. So 1 over z squared plus 2z plus 5 will be less than 2 over mod z squared for mod z big enough. So 1 over mod z squared plus 2z plus 5 is less than or equal to 2 over mod z squared for large mod z. How large we don't know, we don't care, we're going to infinity after all. So, which of course on CR is 2 over r squared. Right, so that's just 2 over r squared on CR. This is true everywhere. Hence, modulus of f of z is less than, well, the numerator is less than 1, the denominator is less than 2 over r squared on CR for large R. Alright, and therefore the integral along CR, I'm going to have to rub that a bit off, is less than or equal to the bound of the function multiplied by the length of the contour, which is pi r, which is going to tend to 0 as r goes to infinity. I'll leave f up here actually. We don't need the picture anymore. Didn't think I could fit these all on one whiteboard. I'm skipping steps and all, of course. The integral along CR f of z dz less than or equal to bound on the function times length of contour, that's the estimation lemma or the ML lemma, whatever you want to call it, which clearly tends to 0. So R goes to infinity. Okay. Hence, put it all together now. What have we got? Well, our residue here, well, the integral over there, let me write it as pi over 2e squared e to the minus I, is the integral along gamma r, is the integral from minus r to r. Whilst parametrizing the line by z equals x, we get e to the I x over x squared plus 2x plus 5 dx plus the integral along CR of f. This integral is independent of r, and we know from our theory, homotopic version of Cauchy-Gaussian, that the shape of the contour doesn't matter, it's just the singularities inside. That's really the residue theorem, I suppose. So I can send r out to infinity. I've just proved that thing disappears. This will become the integral from minus infinity to infinity. Well, technically it's the Cauchy principal value, but for this particular problem, that's the same. So this tends to the integral from minus infinity to infinity, e to the I x over x squared plus 2x plus 5 dx as r goes to infinity. So now we can just take the real part and get the answer we want. The integral minus infinity to infinity cos x over x squared plus 2x plus 5 is pi over 2e squared cos of 1. Cos of 1 radian, remember? We're talking numbers there. And we notice we've got a bonus. If we took the imaginary part, we get the integral from minus infinity to infinity of sine x over x squared plus 2x plus 5 dx is pi over 2e squared. Well, the sine of minus 1, which is minus sine of 1. So a bonus result here. Alright. Let me just repeat the usual warnings. I've said this several times in lectures. When doing these particular problems, you can't look at the integral of cos z over z squared plus 2z plus 5 because cos z is not bounded on the complex plane. Right? It goes to infinity as you go up the imaginary axis. You've got to introduce this exponential thing so that you can keep the numerator bounded. It doesn't work otherwise. And as I said, well, you usually get a bonus out here. That's going to be a 5 there. Okay. What was the other warning I normally give? Oh, yeah, you need to do, there's 3 things to be done, of course. There's the basic setup. You've got to calculate, find the singularities and calculate the residues. You've got to prove that the integral along the semicircle disappears, and you've got to do all the sort of appropriate tidying up at the end. Okay? Not necessarily taking real part. You need to do all these bits to get the question out completely. Well, it's gone 4 o'clock. As I'm saying this live, so I've gone for over now. So I will do just one more question. I'll do one of the integrals over 0 to 2 pi. They're normally a lot quicker than these things. So we get another example to be done. Although, as in 2069, of course, of doing the course, you've been able to see an example of that in my little videos. Hopefully it's a different one I'm doing here. I didn't think to check. And this is from the 2011 exam, I think. Question 6. Yep. Well, the answer didn't look familiar when I got to the end of it. All right. Now, the trick here, remember, is to translate. We're actually going back from the real integral to a complex contour integral, reversing the process that you had when we began doing contour integration. We're going to put z equals e to the I theta, and we can replace the cos and the d theta. But in order to make life a little easier for ourselves, we borrow a trick from the previous type of example. We're going to let I be the integral from 0 to 2 pi, not cos 3 theta, but e to the 3i theta, and then we're going to take the real part at the end. Right. If I'd left the cos 3 theta in as it is, I'd have had z cubed plus z to the minus 3 on the numerator, and give me an extra pole at 0, a pole of order 3. I'd have to find the residue for, which would be a lot of work. But this saves me that bother. I'll just replace that with taking the real part at the end. The usual thing, z is e to the I theta, and we get I is, I'll just write down the thing that you get. Integral around mod z is 1, theta from 0 to 2 pi, of course. That's just going to be z cubed. 5 stays as it is. Cos is, remember, z, for z is e to the I theta, it's just z plus 1 upon z, or at least a half that, so I'm going to get twice z plus z to the minus 1, and then the theta is dz over iz. Is, I've got room to put this, let me just put the tidied up version on here. Take that 1 over I at the front. I prefer to leave it on the denominator, because it's going to get cancelled with the 2 pi I at the end anyway. And we're going to get z cubed dz over, well, let's take out a minus sign as well, because that minus 2 there, 2z squared minus 5z plus 2. Right. So this integral is just going to be the sum of the residues of this thing here. Now, a constant term divided by coefficient of leading term is 1, so the product of the roots is going to be 1. And we're going to find there's going to be 1 inside and 1 outside, that's usual. Don't forget, I mentioned this in lectures a couple of times, these polynomials are hardly ever monic. The leading term is not 1, so you have to be a bit careful with the factorisation if that's the way you go. 2z squared minus 5z plus 2. Well, you could find the roots using the quadratic formula, or you could factorise it. And that's how it factorises this particular one. And once again, simple zeros. So simple zeros in the denominator gives me simple zeros, simple poles of the function. So we need the residue at z is a half, because z equals 2 is outside the contour, so it doesn't play any part. Once again, simple pole, residue f, z is a half, limit equals to half, minus a half f of z, half z cubed, don't forget that bit, over, well, I'll be left with a factor of 2 from that term, z minus 2. Right, that's not too bad. Well, that's going to give me an eighth. Numerator, and twice a half minus 2, which of course is minus 3 halves. So that's minus 3 halves, it's minus 1/24. That's the residue. The other one's outside, so it says it doesn't matter. Hence, my integral is 2 pi I times the minus 1 and I that I left at the front for convenience sake, times the sum of the residues. Well, there's only one. So that's cancels, pi on 12. Take the real part. Well, it is real, so there isn't anything work to be done there. So real part, the integral from 0 to 2 pi cos 3 theta of 5 minus 4, sorry, it's cos theta d theta round 12. No need for any estimation argument, right? The whole thing just goes through. Okay. Well, done well over an hour here, so hopefully that'll be okay. For those of you who are doing MATH2069 this semester, semester 1 2016, for those of you who are looking at this well in the future, I'll be putting up some sort of consultation roster for the couple of days before the exam. Okay, thank you.